All right, so now we're going to finish our discussion of two-state folding equilibria by talking about a monomer-tetramer equilibrium. Again, the energy diagram is going to be much the same as we've talked before. 4 unfolded monomers in equilibrium with a 1 folded tetramer. I'm using Q here instead of T because we use T for trimer. Pass through one transition state, and of course this free energy difference is the free energy of folding. It tells you how much more folded the tetramer, how much more stable the tetramer is versus the monomer, and this is related to the folding equilibrium constant. Or in other words, the folding equilibrium constant is related to delta G through this equation. We could write out this equilibrium. It would involve 4 monomers in equilibrium with a tetramer. If we can also write an expression for the total peptide that's present in solution. This is going to be all of the peptide that's present as monomer plus 4 times the peptide that is in 4 times the tetramer concentration, because each tetramer contains 4 monomers. So if we had 40 micromolar tetramer, or rather 10 micromolar tetramer, we'd actually have 40 micromolar monomer embedded in that tetramer. And so the only 2 things present in solution are the monomer and the tetramer, and that's what we have in this equation. We can define the equilibrium constant as being the concentration of tetramer divided by the concentration of monomer to the 4th power. Through a little bit of algebra, we can replace the concentration of tetramer with the equilibrium constant times the concentration of monomer to the 4th power. Then we can substitute that expression in and subtract p from both sides, and we have this familiar polynomial, the roots of which are going to tell us what m is. By finding the roots of this polynomial, we're going to get an expression for monomer concentration that depends only on equilibrium constant and total peptide concentration. The fraction folded is going to be 4 times the tetramer concentration divided by p, or in other words, 4 km to the 4th divided by p. We're going to, and remember that the expression for the monomer that we're going to get from finding these roots depends only on p, which is a constant, and equilibrium constant, which is temperature dependent and depends on delta G, and we're going to vary delta G such that this equation for fraction folded matches what we observe for fraction folded. Haven't talked to you yet about how what we observe is related to fraction folded, but we'll do that in a future video. And now we'll switch to Mathematica, where I'll show you again how to find the roots of that 4th order polynomial. All right, now that we've got an expression for fraction folded for a monomer tetramer equilibrium in terms of total peptide concentration, equilibrium constant, and monomer concentration, we're going to try to solve the polynomial that we got from the tetramer equilibrium and find the roots of it that will allow us to figure out what the monomer concentration is. So we just need to alter this polynomial a little bit. For the monomer tetramer equilibrium, the expression is 4 km to the 4th plus m minus p equals 0. We want to see what values of m fulfill or satisfy that equation. So we return a shift or shift return at the same time, and we have 4 different roots. Now this gets a little bit tricky here because as you look, the number I does not appear anywhere in these roots. So we don't know yet which of these, if any, are real versus imaginary. It looks like they're all real, but it's possible for some values of k and p, some will be imaginary. In addition, we don't know whether these numbers are going to be positive or negative. We would discount any roots that are negative because you can't have negative concentration, and we would discount any roots that are imaginary or complex because concentration has to be a real number. So to deal with this, I'm going to copy each of our roots. I'm going to get rid of this m equals business. And I'm going to put in some reasonable test values for the equilibrium constant. So I'm actually going to say what k is, and I'm actually going to say what p is. So we're going to let k be something like 10 to the 6. And we're going to have p be 10 to the 6. Not sure whether that's reasonable or not, but we'll imagine the equilibrium constant is large. Then we're going to let the total peptide concentration be somewhere like 100 micromolar. So I'm going to put semicolons there because I don't need it to repeat back to me what k and p are. But now that I've put in some test values for k and p, I'm going to evaluate each of these roots to see, oops, evaluate each of these roots to see whether they are real positive numbers. And so I now press Shift Return, and it tells me that the calculated, this one has at these values of k and p actually is complex, so I won't use that first. Root. The second one also is complex. Actually, it's the complex conjugate of the first one, interestingly. The third root is negative, and it's only the fourth and last root that is positive. So this tells us that at this value of k, when k equals 10 to the 6 and p equals 100 micromolar, you can expect 99% micromolar to be in the monomer state. Interesting. All right, so with that, we will now use this expression. We can plug in this root that I've highlighted to our fraction folded expression for monomer tetramer equilibrium. And we can, p is a number that we know, and k is a number we're going to calculate based on delta G, and we're going to allow delta G to vary with temperature such that fraction folded that we calculate most closely resembles fraction folded that we observe.